Welcome to Science at Work, a new podcast from Savannah River National Laboratory in Aiken, South Carolina. I'm your host, Mike Edelmeyer. Science at Work is a production of the Savannah River National Laboratory SRNL Office of Communications. We usually start the podcast by telling you that this year is quite special in the lab's history. It's been 20 years since the U.S. Department of Energy designated SRNL as a national lab, but you might not know that our legacy spans 7 decades back to the early 1950s and the Cold War. We're trying to build understanding of what a national lab is and what it does so that the non-scientists among us, and I'm included in this, understand how SRNL puts science to work to protect our environment, serve our national defense, secure our clean energy future, and reduce emerging nuclear threats. And one of the best ways to do this, as we have found, is to speak with the scientists, engineers, and other professionals who are at the heart of who we are, what we do, and why it matters. Today we'll speak with Holly Flynn, a senior scientist in hydrogen processing here at SRNL. Holly is a key researcher and technical lead for the lab's work in fusion modeling. Last year she was selected as a Department of Energy Office of Science Early Career Research Program awardee, that's a mouthful, and will receive $2.5 million over 5 years to fund research associated with fusion energy. Sounds like really exciting stuff. Holly's research is important to understand as we hear more and more in the mainstream news and other sources about fusion technology and the benefits of what has been called an abundant energy source. And so Holly will help us understand what her research is about and how it will help advance fusion technology in the U.S. Holly was also one of 8 early career scientists who competed in our first research slam, which meant giving a TEDx-style talk about her work in 3 minutes or less. Let me tell you, that is not easy. We're talking about scientific concepts and principles. Thanks for joining us, Holly. It's great to have you here.
Thanks for having me.
I've been really looking forward to this because fusion is such a big topic in energy research. It seems to have great potential, and we've made great strides in fusion, but there is so much to understand about it. And I'm hoping that, and I'm sure you can, help us with that understanding. Maybe you could start off by telling us about your role at SRNL and what your research is about.
Yeah, definitely. I'd love to. And I'll do my best on informing you on fusion as possible.
Okay.
There's definitely a lot of other researchers here that have different aspects of fusion that they handle with. But me personally here at SRNL, I focus on the fuel cycle modeling. And when I say that, we're talking about processing components, what's going to get the fuel back to the system so you can keep things running up and going. And so our target has been in the past like doing basic reduced models, but also using this software called Aspen, which is heavily used in the oil and gas industry. It's very well supported, but has a lot of stuff built into it that enables us to do like component models built into it. It enables us to understand throughput, so that's like the gas flowing through or other kinds of like forms of gases or maybe liquids, flow rates, those kinds of things, and seeing how that impacts the system as a whole. And the unique thing about this for SRNL is that we have a lot of like decades of tritium research and development and subject matter experts. And the very first fuel that's going to be used in a commercial reactor, I don't think there's any way around it. There's other options, but just how the science works out, and you're going to start off with deuterium tritium.
Okay.
Well, tritium needs to be treated a little specially. It needs to be some hand holding and proper equipment and proper processing, and that's where we kind of come in as SRNL. We have that history and capabilities to understand that and put those components together. And we don't have like a large-scale facility where all those components are integrated. So that's when me and my team comes in and we say, well, we can model this. We can break this out in a virtual environment and build out this system that you can test virtually and understand how those components are going to work together. Get an idea. And then as we build out these models and integrate more complex systems and inform experimenters and the actual like component integration, then that once they start putting that together, that data feeds us and then we feed them. And so it's kind of like a nice little feedback system. And the really big overarching goal for the modeling side of things is to have this big integrated model that not just helps out with design and decisions, but helps out in every stage, including operations. And so that's kind of like our big overarching goal, is to have something that we can guide and inform companies we work with and other researchers and incorporate all this knowledge. But then when you turn that reactor on, those models are still there. Those models are still working and are a power horse to help with control and optimization and understanding what happens with other components. Yeah.
That sounds really, really interesting. What if we take a step back?
Yeah.
And so, if people have been reading about fusion in the news and other national laboratories or other industries, and, the fusion topic comes up, what's important for them to understand about fusion? And I know that might not be the easiest thing to answer in, a sentence or two, but,
Yeah, I think, that's a good question, I think. And I would even kind of step a little bit back and say one of the good things to know, so there's all kinds of parts of fusion. Traditionally, when you talk about fusion, you talk about plasma physics and what's going on, the reaction of, slamming light nuclei together and fusing them together and getting a ton of energy out, and how to confine that on Earth. Because you're essentially saying, let's confine the sun. And you're having to handle these extreme conditions and find out those materials. But we've expanded that out because now we're really interested in commercializing it. Before it was about the physics and getting the physics right and confining that system. Now we want to start producing energy. And I think that's the thing to really know, is that we're opening this area up. There's new curricula being built out. There's new areas of opportunity where we're talking about materials and technology and how to put all that together. And hopefully, and something that's really been a huge topic is workforce development. And I think that's really the information you want to get out there is, we're looking to build this workforce up and have these individuals that can, run these big, powerhouses. And I think, there's all kinds of things we can get into the weeds with fusion. But I think that's what I would say that needs to be known, because we've had these big decrees of a decadal vision where we want fusion within a decades time period. It's coming up. It's not like 60 years in the past. It's, a couple decades in the future. And those are the things I think are the important stuff.
That's really interesting. I keep using that word interesting because this is a fascinating topic for me, because when I see an article in the paper about, it was one of the other national laboratories, I can't remember which one right now, but something, maybe last December or something, it was about a fusion breakthrough. But then later on in the article, it's something about, this other thing won't be for another 30 years. So you wonder, wow, this sounds amazing, but oh, wait, we've got a long way to go. So. Just a comment about that.
I think that's a great comment. And it's one that came up, if you don't mind us talking about it, when that news came out. So what you're talking about is the National Ignition Facility out at Lawrence Livermore National Laboratory.
Right,
yeah.
right.
They have big, huge lasers that are firing at a target, and it's called inertial confinement fusion. So it's a little bit different than us confining things through magnets. So there's kind of like two basic confinement types. And then out of those breed other kind of hybrids and modifications that people are exploring. But they have these 90 plus lasers, or no, it's 100. Anyways, 90 plus, I said. Lasers that are firing at this target, and they have to be so accurate. But they showed that the laser power in was lower than the fusion power out. And so that was a big deal. They call it Q scientific. It just means you're positive, you're net positive energy.
Sounds like a good thing, yeah.
The reason why we're still kind of 30 years out, which is, it's a great thing. It's the first demonstration of that kind of, net positive energy. The reason why we're still kind of 30 years out is that those lasers, probably, I think it's 300 megajoules of energy is how much they use, which is very different than the 2.5 megajoules you got out of the fusion thing. So it's the localized experience of the power in to the power out, whereas the technology and the actual engineering components used up so much energy. And so you have to tackle that problem now. So you've hit a big milestone, big milestone, not to degrade it at all.
Sure.
But there's other milestones we still have to capture now and really hit on. And one of those is the energy that your actual facility and plant eats up or uses needs to be less than what you put out for fusion.
Okay.
So that's why
that
it's still like 30 years out. And so those are the questions we're trying to answer.
That is really cool. I'm interested in your background in terms of, where you went to school, what you studied, and also, well, I'll save this for later, but so where did you go to school? What did you study?
Yeah, so I did some kind of funky little thing when I got out of high school. I decided I wanted to be an FBI agent. So I didn't want to go into science. I wanted to do international relations, and I wanted to go to Washington, D.C. So I packed up and left and went to D.C. for 2 years, where I interned with the Senate and did all this really fun stuff politically. Learned a lot of things, and then I was like in there interning, and they had these tech liaisons that were not in the office, but that talked to, so somebody from these laboratories talked to this tech liaison, and then he communicated that throughout the office to like the senator and incorporated those into all that fun bill making stuff. And
right.
I was like, oh, I don't want to be this person. I want to be the person in the laboratory, So I packed up my bags after 2 years and went to the University of Tennessee, Knoxville. I grew up in Tennessee, Middle Tennessee. And so I did nuclear engineering as my undergrad, and then I got into this program called the Bredesen Center. It's a fellowship program put in place. It's named after one of our governors, put in place that allows you to be a university student, but you work at Oak Ridge National Laboratory.
Nice.
And so that's how you get your PhD. It's interdisciplinary. So I was in plasma physics side of the house, but my friends were like in microbiology, all across the fields. Energy, like batteries and things like that. It was really cool, and I loved it. And getting to work at the laboratory was really fun. And my research scientist out there was my advisor. So that's kind of how that dynamic played out. And it was maybe the first couple years, 3 years, I think it had been going on. So it was a lot of fun. Yeah, it was pretty interesting, different. I wouldn't trade the experience for anything because, people are like, oh, what are your degrees in energy science and engineering? What does that mean? It just means I was in an interdisciplinary program and got to engage with a lot of different individuals and work with a laboratory scientist, which I thought was pretty cool.
That is very cool. So what brought you to SRNL?
Yeah, it's all kind of tied together. It's just like a nice little story that flows together. So I actually met Dave Babineau, who's my, I know this isn't going to mean anything to me, my level 3 manager. And I met him at a conference that I was helping out with in Knoxville, and this was around when I was writing my dissertation. COVID was going on, or about to start going on. It was like one of the last conferences I went to for that period. And he was there, and my research advisor then, he's like, I had a little bit of background in materials, nuclear materials, like fission materials. He's like, I really want you to meet Dave. And so Dave and I chatted, and Dave's like, you should apply to a postdoc position. And he's like, just keep me up to date with it. So I applied to a postdoc position. Wasn't the only place I interviewed with and stuff. So there was another place down in Auburn where I got to continue what I was researching. And I actually really loved what I was researching, so I really, really thought about it. But I wanted to be a bit more hands-on, and and they were also giving me more freedom, which isn't always the case when you're a PhD student, because they kind of want you to focus on your stuff and get through, and that's what you're supposed to do. And get your degree. And so they offered me a lot more freedom to be computational, try a bunch of different stuff. I got into artificial intelligence and machine learning, played with sensors, which I've come to really enjoy, playing with the different data and all that other fun stuff. And so just that appeal. And then they gave me an offer, and I was like, it was close to Tennessee. Had some other personal reasons. I wanted to stay close.
Great.
And came down here and started working, and I've been here for a little over 4 years now. No longer postdoc, full staff now.
Right,
so.
Right. Well, that's great. We're glad to have you. Glad
Thank you.
You're here with us. And so, let's see. Can you tell us how your research might impact our listeners? You probably started to do that already with some of the information about, what do we really need to know about fusion, right?
Yeah. Yeah, I think it's along the same lines. Impact-wise, I think it's that we're wanting to commercialize fusion a lot. And so this is not just like the workforce development I was talking about, but also engaging the public in what we're doing. So fusion is a nuclear energy. So There's a lot of lessons learned we can learn from our, the sister energy, which is fission. There's a whole lot we can learn about it, especially with communicating with the community and being clear and open on what that means. Because even though it's a clean energy or cleaner energy than fission, there's still things we have to be aware of and we have to take care of. Like we talked about tritium, it's a radioactive isotope.
Yes.
Reducing that exposure to the environment and personnel or people, as well as the personnel who are working on it, is very important. It's very important to us, and we're wanting to make sure that's open. We're not trying to, keep things under the rug or anything like. Not saying that anybody has.
Yeah.
It's just, I think that's really important. The community engagement and talking to people and letting them know what's going on, how we're approaching these things, opportunities to engage the community. And just being, clear, like we were talking about earlier in the podcast.
Well, being very clear that it is, there's a lot of opportunity there for, as an energy source, and it's a clean energy.
Yeah.
Which, and that's something that people, I think, understand or want to understand better. How do we get to clean energy versus other types, right?
Exactly, yeah. And I think, those are just really important conversations, and you should have them. And SRNL is really good about engaging the community. We have the Citizens for Nuclear Technology Awareness that a lot of people are parts of. So we go to schools and have those kits and demo things, and I think keeping that going and expanding that is really important.
Yes, absolutely. You're listening to Science at Work, a new podcast from Savannah River National Laboratory. We're speaking with Holly Flynn, a senior scientist with a PhD in energy, science, and engineering, who works in hydrogen processing and fusion research at SRNL. Holly, what can you tell us about the future of this area of research? I mean, we've been kind of talking about some of that, but what would you say is next?
Ooh, what's next? Yeah, I think this is going to go on for quite a bit of time, in my opinion. But next doesn't exactly have to mean in a different area. It could be in your same area. You're just tackling a different question. And I think one of the big things is we've had several workshops. So these places where a bunch of the scientists or individuals, not even just scientists, like Nuclear Regulatory Commission, individuals who are invested and partake in this whole process of fusion and commercializing fusion. And we've had these workshops where we discuss, what are the key research topics and objectives we need to tackle to make this happen, almost planning out a path to commercial fusion. And I think that's it. You just make new objectives and you keep pushing that until you've reached your goal. So
keep pushing forward.
Yeah, you just keep pushing forward. And a lot of stuff has come out of it. So we're working on a fire center proposal, which is a big fusion proposal that the Office of Science, Fusion Energy Sciences has released for different leads. So it's like university and company and laboratory kind of led and engaged, and you're tasked with like working with multiple individuals. Because even though, SNR is really good about tritium science, there's a lot of other facilities and laboratories who have other expertise that you can capitalize on. And when you work together, you're able to make something more cohesive and comprehensive that will drive us toward answering those big research questions. And I think that's the thing, the next question there. For me personally, so my main work is tritium accountancy. Important to know where your tritium is, where it's going, and especially in these big plants, it's going to be a continuous system. So you got it flowing, you've got it disappearing. Not disappearing. I shouldn't say that. You've got it like burning up. You're losing it, but then you're also adding it on top of that. So being able to keep up with that and know where it is, and I really just started this project and using artificial intelligence and machine learning to really capitalize on how to do this with sensors. So it's kind of sensor fusion. So you're just taking a bunch of sensors and you're fusing their information together, and you're teaching like a program how to keep up with the tritium in the system. But I'd love to keep, even if it's not like in fusion, I'd love to continue that kind of work. That would be something I'd be very into, even if it's in fission accountancy or something along those lines, or control dynamics in other systems. That stuff is awesome. I love that stuff.
It sounds pretty awesome. So it sounds like that project may continue for, a while.
Yeah. It's going to continue for 4 more years for sure.
Great. Wow. That's really cool. So, in addition to getting to know you and your work at SRNL, I think we'd like to get to know you as the individual. And, there's a lot of ways to tackle that. But I would say, or I would ask rather, what is one thing that we should know about you that influences the person you are and maybe the approach that you have to your work?
Yeah, I think this is like a double-edged sword, as you can see with my comments. They're a little long-winded. I'm very excitable, so I get really excited. It doesn't, always rub people the right way, but I feel like the right people, it rubs the right way. So
I think it works perfectly in this situation because you're passionate about your work.
Yeah, I think it's well. And, my husband always tells me, he's like, don't feel bad about being excited about stuff. He's like, people who don't like that, he's like, that's crazy.
Yeah.
I'm like, well, we'll see. But yeah, so I'm extremely excitable. So I like to talk about things, and I can sometimes go a little overboard with talking too much. I think that's it. But what comes out of that is I really like to go to, it's almost like building a little Lego set with me.
Mm-hmm.
I want to work on the foundation. I want to understand what I'm working with and then build up from there. And I think that's where, that's one of the benefits of my excitableness comes from is starting with a simple system, because I think a lot of people just want to go straight to the end and be like, I just want the result. And I'm just like, I really want to know exactly what I'm doing. Maybe not exactly, but start with a simple system, get that going, build out, also working with people. I love it. Building out a team environment where we just, collab in the cube and talk about things, and they have ideas and they get to run with them. Seeing that happen has been really awesome, just from this program and this, working up this modeling stuff. So, yeah, all that fun stuff.
That's a great answer. That's a great answer. Well, Holly, thanks for being with us today and sharing your expertise. It's really important for us to know about. And thank you all for listening to our podcast. Science at Work is a production of the Savannah River National Laboratory in Aiken, South Carolina.